Hi, so welcome everybody. We are going to tell you about GraphFrames and we're going to tell you about TinkerPop OLAP. Just to start out with, I am Russell. I love distributed systems. I spend a lot of time writing the integration between Spark and Cassandra. And Artem is a fellow expert of mine at DataStax who spends a lot of time writing algorithms for Graph OLAP and all kinds of fun stuff like that. And in case you didn't know what TinkerPop and GraphFrames were, and you just came here because those sounded like some interesting words, they're both frameworks for doing analytics on graph. And one of the cool things that they both share is they can both use Spark as an underlying framework for their execution. And in case you don't really know what graphs are, let's just quickly go over that as well. Graphs are basically a collection of vertices and edges, and if you're confused what that means, vertices are basically things. Usually they represent, something like maybe ships. And we have all these different ships, and each of them can have a whole bunch of properties that say certain things about them. And then the edges are the relationship between these things. So usually when we're talking about a graph, we're talking about things and the relationships between them. So in this case, we have these edges up here that I've got a specific label, and that label is succeeded by, so that not only do we have this relationship between these ships, but we know what kind of relationship they have. So this is all well and good, but it can become even more interesting because we can also label our vertices. So that this doesn't just have to be a graph that has only spaceships in it. We could also actually include the crew. And if we do that, we can now have a graph that not only has information about ships, but it can also have information about how the crew of these ships relate to the ships and to one another. So with this, we end up with this really nice, complicated set of relationships where it's really easy to trace paths through this graph and answer certain questions. And that's really why we want to do this, because you might be looking at this and be like, why do I want to have this big mess of vertices and relationships, and they're all over the place, and I have all these different labels? And the reason is that we can ask questions that in a relational world become very difficult to actually express. So asking things like, what captain served after Kirk, or what ship was 2 after the NC-1701, become pretty easy to answer when we look at a graph. Because in this graph, we can do something called a traversal, where we basically follow the edges in the graph from one node to another, and we can answer a question. So for example, if I want to ask that question about who was the captain after Kirk, I could start at the Captain Kirk node, find out what ship he served on, find out what ship was succeeded, what ship came after that, and then look at the captain of that ship. So basically, by just doing this little walk through the graph, which I can basically describe in English, we can get the answer to our question. We don't have to worry about joins. We don't have to worry about normalized forms. Everything is basically present in the data itself. So, and just an example of what ship was 2 after the NCC-1701, we just follow that succeeded by edge 2 times. And if we follow it 2 times, we know the ship that came 2 after wherever we started. So the reason that we want to talk about TinkerPop right now is that TinkerPop is one of those many graph API and languages that you can use to actually do these kind of traversals and express these kind of paths when we're working with graph data. TinkerPop itself contains a whole lot of different things. One of the important things is that it has that Gremlin traversal language, and also it has this thing down at the bottom you see where it says Graph Computer, and this is where we can actually interact with various different execution engines, including Spark. And we'll go into that in a minute, but first let's give a few examples of how Gremlin actually does its traversals with Artem.
And now we are in another universe when I will get a MovieLens example, MovieLens dataset that show users that rate movies. And so that user has occupation and movie have genre. And well, here is an example of that, sample of that graph. So we have a Terminator movie here, that is sci-fi, Star Trek, that's a sci-fi, and Screamers and sci-fi, and users that rate them. And so the users has occupation like students, artists, programmers, and so on. So let me switch to the studio. It's a DataStax studio to work with the graphs. And well, actually, what we will do, we'll ask question to our graph. And in this case, it will be OLTP questions that are vertex-centric. And we can, well, that is how I generate this subgraph. I will probably return later to this query. So let's start with some simple query. Say, what Star Trek movies did a user rate? And we will start with in this case, we will always start with a graph, with the vertices, and with vertices that has user ID 710. And we will traverse to the movies with the rated ages by out, and then we will find Star Trek movies in it. So we will find them. So, and we will see that users see 9 Star Trek movies. Well, actually, let's see what happened. Let me show how the traversal look like. I will add pass and unfold step just to get the pass of the traversals. And you will see that the traversals are really simple. We start from the users and go by rated ages to the movies. So let's add one more step, and we get the genre of that movies. In this case, I will just add our genre here. And well, graph looks a little bit messy, but we start with the users. Users go to the movies, and movies has genre like action, sci-fi, adventure. That's still really simple thing. Well, more interesting thing is what was the ratings. And in this case, we will start with the users, get the age with name rated, and I will store the part of the pass as rating, and then we'll go to the vertices, and well, again, we'll filter out all the Star Trek and save it as a movies, and then use a select word to select movies and rating by name and by stars. And we can see that, well, our user likes Star Trek 6 and hates Star Trek 5. That surprised me. So I will switch back to the Russell here, and here we'll continue.
Yeah, so that was an example of how you can use the TinkerPop language Gremlin language to ask these OLTP questions. But at a certain point in time, your graph might become so large that you can't do this in an OLTP method. You actually need to start doing something bigger. And this is where Spark starts coming into play. So TinkerPop's OLAP mechanism basically works a lot like the OLT mechanism, where it starts at a single, in the OLTP mechanism, it starts at a single vertice and then follows out edges. In the OLAP method, it actually starts at all vertices at once and then has them all step simultaneously, and basically is running this traversal from all the vertices at the same time. So obviously, to actually do this, we need to have some sort of partitioning, because we can't do big data without some sort of partitioning. And the partitioning that TinkerPop does is it builds these pair RDDs. And I know this is probably the first time in the conference that you heard someone talking about pair RDDs, but this is basically the underlying primitive that TinkerPop OLAP is going to use to actually spread out our data. And it's going to spread it out in a way where each vertice and all of its adjacent edges are stored as a value, and its identifier will be stored as the key. So this means that we have this representation here where every single vertex and all of its adjacent edges and all of their properties will be co-located in a single Spark task. Now you might wonder, well, with all that set up like that, how do I actually get from one vertex to another? Because I no longer have a direct connection to them. I just have all of the edge information. And that's how the mechanism for this actually works, is that we start out with a graph computer traverser on every single vertex. And we use a Spark accumulator to store some global state that belongs to the traversal. And then every time we need to take a step, we do a shuffle. We basically take the messages that would be outputted, which is where is this traverser going to go next, and we use a shuffle to move them to their new vertices that they're going to be landing on. So every single time you go out inside of a traversal inside of OLAP, you end up doing a shuffle. So you would do that over and over and over, depending on what algorithm you're running or whether or not you're running a traversal. And eventually, the resulting graph and resulting state can get combined and are returned to you as a result. So the things to notice in this pattern is that we basically have to do one shuffle per hop. And now Artem's going to show, with the same exact language that we were showing before, Gremlin, how to do some OLAP traversals.
Right. Let me switch back to the studio. And now we will in OLAP world. And well, I will do a snapshot of the graph just to make a little bit, to run a bit faster in memory, in Spark memory. So this time we will start asking another kind of question. So that will be OLAP question. So how many movies are in a data set for each genre? In this case, we will start with all genre vertices with that has label genre, out with genre to the start with the movies and out to the genre, and then group count them. That's classical things that you do in any OLAP. And we'll group count by name. And you will see that most of the people watching drama. And well, sci-fi is not so popular here. But who is watching sci-fi? Because it's much more interesting. And in this case, we will build a really long traversal. We will start from the genre, go to the movie, go to the users, and go to the occupation. And then, so we start with the genre, sci-fi, go to the movie with the genre's age, go to the user with the rated age, in the opposite direction to the age, and go to the occupation, and group count by name. And you can see that, well, usually students watching sci-fi, and, well, programmers are in the first place. What else we can ask? Well, what programmer watching we can ask if they don't watch sci-fi? And in this case, we'll go back in the back direction, all the same thing. So we start with the programmers, go to occupation, go to the movies, start with the occupation, go to the users, go to the rated, go to the movies, and go to the genre, and group count by name. And we can see, well, actually, programmers watch a lot of sci-fi, after all. The result is much better compared to drama. But what is so let's back to the Star Trek. What is the average rating? We know that users 710 don't like some of the
Star Trek 5.
Yeah. Okay, so in this case, I will use another way to get the different subqueries. I will start with the movies and then project names and ratings. So names will be gathered from the movie values, but rating we will get from the subquery going to the age rated and get stars from them. And, well, calculate the average with a mean. And in this case, we will see that, well, no one likes Star Trek 5. Well, that's all examples for the TinkerPop. So let's switch back to the Russell.
Yep. So we just saw how the TinkerPop OLAP traversals basically use the exact same language that we were using originally for the OLTP queries. All that basically changes is that we specify a different execution engine. So there are some pro-cons to this method. So some things you might have noticed when I was talking about this is I was talking a lot about how all of the edges that are incident on a vertice are partitioned with it. Now this ends up being a big con if you have an extremely high degree vertice. That is, you have a vertice that has lots and lots of edges. Because if you have too many edges, so for example, you might have a vertice that is labeled China, and you have all of your users who live in China connected to that vertice, you might have one that no longer can fit in memory on a single machine. So you can end up with some issues there. But on the pro side, every single time you want to do a message pass, every time you want to send a message from one vertice to another vertice, it's only a single shuffle. So that's really a good deal if you're doing something that requires a lot of hops along your graph. So some other things is that it's very flexible. We have all of this direct access to our edges and edge properties. So there's a lot of good things here. But let's say you want to go into a different system with a different set of trade-offs. So GraphFrames kind of exists to complement this kind of method. So instead of working the way that TinkerPop OLAP does, it has different partitioning and is basically a pure dataset data frame API that you can use with Spark. So under the hood, the biggest difference here is that it doesn't need a graph storage. it can work with any relational database under the hood, and that's relational as in rows and columns. So for example, whenever you're making a graph frame, you only need two different sub-data frames to build it up. One is your vertex data frame, and the other is your edge data frame. And within these two data frames, the only columns that you are required to have are the ID column for your vertex and the source and destination columns of your edge data frame. So this is my tiny little example graph where we just have this one relationship between these two characters. One thing you'll notice here is that inside of this representation, actually specifying different types here, or well, the only types that we can have here are Spark primitives, Spark catalyst types, and that there is no actual definition of a label on either the vertices or on the edges, which means that if we store different types of information inside of our vertex table or inside of our edge table, it's up to us as the user to define what kind of thing it is or what properties actually apply to that particular vertex or edge. So one of the biggest pros of working in GraphFrames is that anything you do in GraphFrames is going to basically run through Catalyst at some point, so you get a lot of those optimizations that come with all of the great things in the DataFrame dataset API. So that's really exciting, and it also lets us combine our data that's inside of DataFrames with any other DataFrame compatible source. So if you are working in GraphFrames and you do a traversal or you do a count, it's very easy to take that data and feed it into any other DataFrame thing like MLlib or connecting it to another source like a MySQL database and writing out the results. So this is just an example of how the basic motif matching algorithm works inside of GraphFrames. So GraphFrames has its own kind of traversal, its way of describing the relationship between vertices, and they basically function like this. So you'll notice up here I've written this kind of cryptic little text where we have an A and some parentheses, we've got an E in here and a B, and that basically is representing a triplet inside of my graph, where I have a node A that connects via edge E to some node B. So the way that GraphFrames is actually going to build this up, if I do this motif lookup, is it's going to start out with our vertex data, and it says I need to make A. I need to make A to actually start one of these triplets. So it will take our vertex, and it will take all of the rows there and basically put them into a UDT labeled as A. So pretty simple. We now have our start vertices. We then need to get all of the edges that are incident on those particular vertices. And to do that, we need to do a join. We have to join with our edge data frame. So we end up joining with the edge data frame, and the value for the AID matching the edge source is our join condition. And now we end up with a data frame that has two columns. One UDT, which is A, which is our start vertex, and then another UDT, E, which is our edge data. But of course, we still don't have B yet. And to get B, we actually have to do another join. So we end up joining once again with the vertex table, and on the condition that the destination of the edge that we just picked out is the ID of the vertex that we're going to. And we end up with this wonderful data frame at the bottom where we have three columns, one representing the start of an edge, one representing the edge itself, and one representing the destination of our edge. Now, one thing that you've noticed here is that we had to say join twice, and that's two joins when before we only had one join, and everyone knows that joins and shuffles are scary and terrible, and we don't want to do them ever. But there are some things that we should know here that can make these joins not as painful and make this actually a really great mechanism for doing some graph algorithms. And that's that all of those optimizations that happen inside of Catalyst are still going to happen inside of this plan that I've made. And that means that even though I have these two join relations here, and I have all of this logical plan, if I put in predicates, or if I put in different other things, they're actually going to get propagated back to my sources. So for example, if I want to only select the ID of the beginning of my tuple, or my little triples here, that will actually go up through my plan and get applied at every single layer to whatever sources that actually it can be applied to. So predicate pushdown basically happens implicitly with anything I do as long as my underlying sources support it. And those joins there can be transformed into broadcast joins, because Catalyst is able to look at this plan that's been created and say, oh, well, this particular join might be against not a lot of data. So for example, if we filtered our bottom data frame here and said we're only interested in edges that have a property of seceded by or something like that, that property might trim down our edge data frame enough that it can be joined via broadcast join instead of a full shuffle join and end up saving us a lot of time. So this kind of stuff all happens automatically under the hood, and it's pretty great. And of course, we also get all of that great code generation that everyone keeps talking about. All of this stuff can get glued together and put in with unserialized operations on the actual binary as it's going through. So we can end up taking we can get a lot of advantages over a system that's actually working with serialized Java types. So this is all super cool. And now Artem's going to show us a few examples of how you can actually write some of this.
Right, now we are in another notebook, that's Zeppelin and Spark. And we will start with GraphFrames. Well, actually, DataStax support loading GraphFrames and TinkerPop graph from the same source. So I will load graph with our secret source here. And well, actually, as Russell said, GraphFrames is just 2 data frames. So we can count them, say, graph vertices count and get count, and graph edges count and get count. And we will do all the data frame thing with that. For example, we can show some sample of the graph frame. And you can see that I have to have an ID column for the vertices. And well, I add label because we have labels in our data sets. And all other things are also represented in a vertices data frame. And in edges data frame is the same. I have to have SRC and DST column, and they are hard-coded into the data frames. And then label and other thing I need for example, stars, I have in some of the vertices. As you can see, rated has stars, but occupation has no, but because there are only 2 data frames, I have to do all the things. So let's ask the same question we asked before. What program are we watching? In this case, we will use all these kind of triplets. Users to occupation, users to movies, movies to genre. And in this case, I will check that our occupation age has a label occupation, our rated age has a label rated, our genre has a label genre. And well, filter out occupation by programmer. And then I will use a data frame group by. So I will group by genre.name, because genre is a struct. And count and show. And we will get the same numbers here. So, well, actually, it will do approximately the thing. And you can write it in SQL. But this SQL is for the proper database. But because we have only 2 data frames, the SQL will look a little bit different. So let me just make two table view for vertices and for edges. I will name it V and E, and write SQL against them. And I will ask the same question, what program you're watching. So in this case, I will need to select genre name and count all this. So, and I will do that join from occupation, from E to, I cannot read it, sorry. There are a lot of joins, 6 of them. And then, well, actually, I do absolutely the same filtering you see before. So, well, actually, the GraphFrame Motif finding is a synthetic sugar for this kind of joins. And, well, actually, I get the same picture here. But as Russell said again, that the main strength of the GraphFrames, I can join the data with any data sources. Cassandra, MySQL, TSV. So, for example, let's imagine we have a data frame with names, and we know that user 710 is Russell. And we can join these names with our vertices. and create new graph frame with these new vertices and ask what user Russell watching and how much films. And we can find that it's, wait a moment, it's more than 800 films, movies, sorry. That's, well, surprised me a lot. Well, and export is also really simple. So you just can get this data frame and write it out to the file. In this case, it's Parquet. Oh, and to do the same with the edges. And well, actually, you can import that data back as simple as that we exported. So in this case, I can use, for example, just select data from any data source. In this case, I select vertices. And I need at least IDs here. And I select edges, and I need at least SRC and DST columns here. So, well, the other important thing with the graph frames, it has already had a lot of graph algorithms. And it's really simple to use them. With one string, you get one of the graph algorithms. And the last thing I want to mention that, well, in data stacks, you can mix both of them. You can start with a pretty simple traversals, get a data frame at the end, and do the data frame methods on it, and get the same result. That look a little bit, so that looks short at least. So let's switch to the Russell to wrap up.
Yep. So we saw that in GraphFrames, we have some different trade-offs here. One of our pros is that we're going to be much faster on basic counts, things that are able to use Catalyst directly. We're going to be a little bit slower on our more complex traversals. If every time we have to do a jump, if we're using all of the data, that means we have to do 2 shuffles every single time. But again, it's also very easy to connect to other sources, and we get all of those great Catalyst benefits. So basically, in wrapping up and saying choosing the right framework, it's really hard to say a generalization. It's best to kind of think about what problem you have. So for example, if you've got long paths, if the kind of algorithms that you want to do in your graph require using all of the vertices and passing messages from all of them to themselves over and over and over again, the TinkerPop OLAP is probably going to be a more efficient method for doing that in. But on the other hand, it's going to be a problem if you have very high degree vertices because of the partitioning that I mentioned before. On the other hand, choosing GraphFrames is really good if you're doing a lot of basic aggregations or you're connecting to any other source that isn't TinkerPop compatible, because you can read in graphs from just about anything that is data frame compatible. But longer path algorithms are going to have that additional cost every time you have to do the extra joins. So I, of course, would be remiss if I did not tell you that you should check out DataStax Enterprise, where we allow you to use both of these right out of the box. And not only that, but we write it. And we show, as Artem showed you, we actually have been working on adding a Gremlin-like API on top of GraphFrame, so you can actually run TinkerPop-style traversals on GraphFrame data. Yeah, so that's about it. If you want to learn more about graphs, please check out DataStax Academy Graph course. It is completely free. You can try out DataStax Enterprise, because that keeps us employed, and Apache TinkerPop link and GraphFrames link, in case you're interested in reading more about those things. So thanks, everybody. And if you have any questions, we have so much time left.
Yeah.
Are you looking at RDF and Sparkle at all in any capacity?
Not really.
No,
Sorry.
Okay.
How easy is it to go from one to the other, like export from GraphFrames, import in TinkerPop, and the other way around?
So I would say within DataStax Enterprise, it's pretty easy. But outside of DataStax Enterprise, the two basically have different formats and different serializations for actually representing their graph data. I don't know, Artem, you have any further details on that?
Yeah, well, actually, I have details only about DataStax because we develop it. And so in DataStax, it's just one line of code. You say export, save vertices to the graph, and you save and then save into the TinkerPop, or export data from the from our storage and get a graph out of that. So,
Yeah.
but right in a.
I would say the most complicated thing about it is that in TinkerPop, you're basically allowed to have whatever you want inside of your vertex. It can be any Java object connecting to anything, which doesn't necessarily have to have a serialization that would map directly to a GraphFrame. Although in DataStax Enterprise, we've got Cassandra under the hood, so we have a restricted schema and type system. So we can do that okay. One more?
Yeah, I was wondering, do you have a feeling at what scale does it make sense to use these tools versus like just bringing the keys into a single machine solution like Neo4j, doing the graph analysis there, and then joining that from the keys, looking up the real data?
Well, actually, you answer your question. If you have data that feed into one machine, you should use any in-memory library like iGraph, Neo4j. But if you have for graph algorithms, you probably need some of that. But if you have a real big data that doesn't fit into one machine and really doesn't fit in memory, that's the only solutions probably. So you need, it's a different, level of the solutions. More about traversal. So usually we even recommend, so you can get a subgraph with our solutions and export and run it, so in R, do advanced analytic on it, and then save result back. And actually we have this integration also with Spark.
That's a great pattern, thank you.
And we're out of time for questions. The track will resume after lunch. Thanks to the speakers.
Thank you.
Everybody, thanks.